Now, we're going to change the topic completely. I'm now going to ask you the question, and I will answer it for you. Why is the sky blue? Why are clouds white? And why are sunsets red? We all know that sunlight is composed of many colors. When you see a rainbow, you see that the white light from the sun decomposes in colors. When that sunlight goes through air, which contains very, very small particles, smaller than 1/10 of a micron. A micron is a millionth of a meter. 1/10 of that is even 10 times smaller. But it has to be even smaller than that. Smaller than 1/10 of a micron. Then, of the white light from the sun, light will scatter off those small particles, and the blue light that is present in the sunlight has a 6 times higher chance to scatter than the red light. That phenomenon is called Rayleigh scattering. And in our atmosphere are many particles which are that small, which are smaller than 1/10 of a micron. And so, I will now make a drawing. I can still do that here. So you're standing here. This is the atmosphere. And the sunlight, the sun is there, very far away. Sunlight is coming in like this. You look at the sky, and what do you see? You see scattered light, but what do you think the color of that scattered light is? What is the color of that scattered light? It's blue. Because blue has a higher probability than anything else. So it looks blue in this direction. If you look here, it's blue that is dominating. If you look here, it's blue that is dominating. If you look here, it's blue that is dominating. Unless you look straight into the direction of the sun, you will see that almost everywhere the sky is blue. But now comes the question, why are clouds white? Well, the particles in a cloud are small water drops. They are 5 microns or larger. And when particles are that big, Rayleigh scattering is not operative. Blue light is no longer preferred to scatter, but all colors, all the colors of the light of the sun scatter by the same amount. Well, if you see all the colors from the sun coming in your eyes, you see white light. That's the idea of the mixture of all colors. So that's the reason why the clouds are white. So here's a cloud, and the light of the sun strikes it. The small water drops will scatter the light, but it will be white. Now, when it's really bad weather, you may have noticed when you hear and you look up to the cloud that they're not so white at all, that they are actually on the dark side. That happens. Not always, but it happens. The reason for that is that then the clouds are just too thick. Clouds also absorb light. And so if the cloud is thick enough, well, then so much light is absorbed that comes in from the sun that the bottom just becomes dark. But that same cloud that would look dark from below, if you flew over with an airplane, I guarantee you that it's white. That scattering, by the way, of large particles, which gives you no preference for any color, we call that me-scattering. I'm going to demonstrate this to you first using cigarette smoke. I have here a floodlight which shines light straight up. I just turned it on. And we're going to make it very dark in the room. So there's only this light going up. You won't see that light because you can only see the light if it changes direction from going this way to this way. If it doesn't do this, it doesn't come in your eyes. Well, I will make it go in your direction because I'm going to put cigarette smoke here. And in cigarette smoke are many particles smaller than the tenth of a micron. Blue light will come in your direction. Now there are also particles which are substantially larger than the tenth of a micron. Tough luck, they will show you white light. But what you will see, that the overall impression of that light that came up here, scattered in your direction, the overall impression will be that it is bluish. And that I want to bring first to a test. So, I need some cigarettes, because I need some smoke. I hate this experiment. This is really a terrible experiment. Well, we talked about the sacrifice for the sake of science, right? I really need smoke. All right, Bill, you can make it dark. Okay, now try to be a little kind to me. Try to make it see bluish. But be honest at the same time. Who agrees with me and says, yeah, it is bluish? Say yeah. Okay. Those of you who do not agree, say no. Well, the yes have it. Now I'm going to convince the no's how wrong they were. I'm going to take the smoke in my lungs. I'm going to inhale it. And in my lungs is a lot of moisture. And so water will precipitate on these very, very small particles, the ones that gave the blue light that were smaller than a tenth of a micron, and these particles will grow in size, and before you know, they are much larger than a tenth of a micron. Then I will blow that smoke out. It has to be white, because they're no longer small particles. So if I hold the smoke into my lungs for a minute or so, and I blow it out, it will be white. But before I blow it out, I want you to see the difference. And so just before I blow it out, I will first show you this again, so that you can compare. And then I will blow it out. It's one of the worst experiments I've ever done. But you see the color change? No question, right? Even though I agree, the first one wasn't really blue, not as blue as the sky, it was bluish. I want to show you two slides now of Rayleigh scattering in a very different way. So Bill, if you can turn the lights off, and if John can give us the first slide. You see here a cluster of stars. It's called the Pleiades. I'm sure all of you have heard about the Pleiades. It's about 400 light years away from us. And these stars in this cluster are very hot, hotter than the sun even. They produce very clear white light, but they are surrounded by very fine dust. And so the light from the stars is scattered in your direction, because the photograph was taken from your side, and you very clearly see that that scattered light is blue. So that blue that you see is a straightforward example of Rayleigh scattering. Next slide, please. Here you see a man on the moon. Now there's no atmosphere on the moon, so the moon doesn't have a blue sky. But astronauts that walk on the moon have a package on their back to cool them, because it can be very hot on the moon. And there is always an exhaust of water vapor. And since the moon is vacuum, this water vapor immediately evaporates and turns into exceedingly small water drops, apparently small enough that the light that scatters off them becomes blue. And so this astronaut, when he looks at the sky, is completely black, has created around himself his local blue sky, which is the result from the fact that he is wearing this cooling pack. Remarkable, when I first saw this, remarkable how this Rayleigh scattering makes him create his own atmosphere. Can I have the lights, please? Why are sunsets red? Well, when the sun is high in the sky, about 1% of the sunlight is scattered. Comes from above, comes in this direction. You're standing here. And so the amount of atmosphere that it has to go through is relatively small. When the sun is only 5 degrees above the horizon, so the sunlight comes in this way, then already it has to go through a much thicker layer of atmosphere. About 10% is being scattered, by the way, at 5 degrees. When the sun is near the horizon and the light comes in this way, then it has to go through an unbelievable thickness of the Earth's atmosphere. Just a matter of geometry. The thickness is so enormous that all the light that was blue in the sunlight has been scattered out already. So whatever is left over, the only color that can make it through is red. And that's the reason why when the sun is so low in the sky, whether it rises or whether it sets is irrelevant. That's the reason why the sun turns red. And if there were here a cloud and the sun were there near the horizon, this side of the cloud will turn red. You can clearly see that in the sky. So the interesting thing is the same reason why the sky is blue is why the sun is red when it sets. Because the blue light has been sucked out by this huge layer of atmosphere that the sun has to shine through. The moon does the same thing when it rises and when it sets, also red. Stars and planets do the same thing. You may not have noticed it, but when Venus just comes up over the horizon, just red, beautifully red. The dirtier the atmosphere, volcanic eruptions, the more beautiful are the sunsets. The more pollution in the air, the more beautiful are our sunsets. I want to show you the next slide, my last slide. Can we turn the lights off? This is something truly amazing. This little piece, this solid piece that this person holds in his hand is called aerogel. It weighs, the density is only 4 times higher than the density of air. Imagine a solid with a density only about 4 times higher than the air. It contains of silicon dioxide particles which are way smaller than the tenth of a micron. So they are ideal for Rayleigh scattering. And look at it. The light that comes from above is scattered in your direction, and what do you see? Blue light. There it is. This is blue. Light comes from above. You see a shadow here. But it is so thick that when the light emerges, all the blue has already been removed, so what is left over? Red. That's the reason why sunsets are red. You see that here. You see here in one slide why our sky is blue, and you see why our sun, when it sets, is red, with 1 piece of aerogel. An amazing material it is. Yeah, I can have the lights again, thank you. I now want to create for you in the lecture hall blue light, a blue sky, and a red sunset. If you're sitting here, you're lucky, then you will see it very well. If you sit there, you will not see it so well, but look, you get what you paid for. I have here a bucket of sodium thiosulfate. If I put in that liquid, which is very transparent, looks like water, if I put sulfuric acid in here, then sulfur will precipitate. And these sulfur particles are smaller than a tenth of a micron. And so the light that will come from this gun in this direction, that light will then, due to the sulfur, scatter in your direction, and you will see it blue. So you will see the blue sky right in front of you. That's why I put you in, Neil, that you would see it so well. You won't see it so well, although even at an angle you might see blue. But this is only part of the demo. That's the sun. This light goes through this liquid, and that's the sun. And now I'm going to add H2SO4, sulfuric acid. The sky will become blue, but in time, more and more and more and more sulfur will precipitate. That means the light has to go through thicker and thicker and thicker and thicker layers of these particles, which is equivalent what the sun is doing when it's low to the horizon. So what do you think will happen with the sun? What?
It will turn red.
It will turn red. You are fantastic. Okay. So I will first put in the sulfuric acid in daylight. And then I will stir, and then we'll make it dark, and then we need patience. I will stir a little. Let's make it dark. And now, be patient. The bluer the sky, and it will very shortly turn blue, the more the color of the sun will change. Right now, sun looks quite normal. 3 o'clock in the afternoon. Hey, I see the sky turning blue. Who can see it too? Yeah, you see, it's more difficult there. You can really see the sky turning blue. That's Rayleigh scattering of these very small sulfur particles. Hey, look at the sun. It's 4 o'clock. It's clear. It's no longer as bright as it was. It's clearly turning slightly reddish already. Who would have thought, ever in your life, in a lecture hall of MIT, to see a red sunset? Isn't that immensely romantic? Outsiders think of MIT students, and that includes even professors, as nerds. Well, to create a red sunset, it's not very nerdy, is it? Isn't this beautiful? Look at the sun. And look at the sky. It's past 7 o'clock already, you can tell. To be frank with you, I think we are getting very close to sunset. Yeah, yeah, yeah. Lights. I hope you'll bring your musical instruments a week from today and send me email. And then we'll agree on which instruments we will choose. I hope you have a good weekend. See you Monday.